All right, chemistry, this is your video lecture for chapter 4, section 1. In this section, we want to be able to explain the mathematical relationship between speed, wavelength, and frequency of electromagnetic radiation. We want to be able to discuss the dual wave particle nature of light. We also want to be able to discuss the significance of the photoelectric effect and line emission spectrum of hydrogen to the development of the new atomic model. And lastly, describe the Bohr model of the hydrogen atom. So let's start with light. Electromagnetic radiation is a form of energy that exhibits wave-like behavior as it travels through space. Together, all the forms of electromagnetic radiation form the electromagnetic spectrum. I'm sure you've seen a diagram like this before, showing all these different types of light that have varying wavelengths, from low to high energy. And I'm sure at some point someone has pointed out to you that the portion of the electromagnetic spectrum that the human eye can perceive is actually very narrow. Okay, we're somewhere in the wavelength of 10 to negative 7 to 10 to negative 6 meters as far as the wavelengths that the human eye can detect. Everything else is going to be undetectable.
Amplitude is the height of the wave. It is the maximum distance that the particles of a wave's medium vibrate from their rest position. Wavelength is the distance from any point on a wave to an identical point on the next wave. Period is the time it takes for a complete cycle or wave oscillation to occur. Frequency is the number of waves, cycles, or vibrations produced in a given unit of time. Wave speed is calculated by multiplying frequency by wavelength.
Here, one more look at the electromagnetic spectrum. We just represented mathematically how to calculate frequency or wavelength. Again, these numbers here are representing wavelength measured in meters. So notice that these are very, very small numbers. These are very small distances. Just look at some of those terms specifically. Wavelength, represented by lambda, is the distance between corresponding points on adjacent waves. Frequency is actually not represented by a V. It's actually represented by the Greek letter nu. You can kind of think of it like a cursive or italicized V. But frequency is defined as the number of waves that pass a given point in a given or a specific time, usually 1 second. Now, you can put in whatever unit of time you want there. You can watch to see how many waves pass a given point for an hour. You can sit there for a day. It doesn't matter. It's just a given unit of time. But typically, when we're talking about the electromagnetic spectrum, we're looking at 1 second as this unit time. Frequency and wavelength are mathematically related to each other by the equation C equals lambda times nu. In this equation, C is the speed of light, which we've already dealt with this year, measured in meters per second. Lambda represents the wavelengths of those electromagnetic waves, measured in meters. And nu is the frequency of the electromagnetic wave in per seconds. That -1 in the exponent simply inverts the seconds. It's 1 over seconds or per second, also known as the unit hertz. So here we have a graphical representation of wavelength and frequency that relates to the small video that we just watched. The distance between any two corresponding points on one of these water waves, such as from crest to crest, is the wave's wavelength. We can measure the wave's frequency, represented by nu, by observing how often water levels rise and fall at a given point, such as this post that we've picked right here. The photoelectric effect is very important to developing this new atomic model. Okay? Now, we've started in this course, starting with John Dalton's solid sphere model. We talked about a few different experiments that led to the creation of additional models like J.J. Thomson, Ernst Rutherford, and their models. But we're actually now moving towards the present day model, which we now refer to as the quantum mechanical model. But one of the big things that allowed us to get to this point is the photoelectric effect. Now, this was described by Albert Einstein. It's actually the reason that he won his Nobel Prize. But the photoelectric effect is fairly complicated in terms of what's going on. But what we need to understand for this particular section is that the photoelectric effect refers to the emission of electrons from a metal when light shines on the metal. What this photoelectric effect does for us is it allows us to measure the minimum quantity of energy that can be lost or gained by an atom. We call this minimum amount of energy a quantum, which simply put is kind of a generic word describing a unit, a chunk of something. Now, how does the photoelectric effect work? Well, we're shining light on some metal. So electromagnetic radiation strikes the surface of the metal, and it is that light, or more specifically, the energy from that light that is ejecting electrons from the metal. How do we know that electrons are being ejected? We can now see an electric current where before we could not. Okay, so we have this voltage source, we have an anode and a cathode. They're not going to be connected. There's going to be open space in between those two items. But when we shine light on that metal plate, as long as it has a minimum frequency, okay, a minimum energy, it will begin to eject electrons, and those electrons will move towards the anode, completing that circuit and generating an electric current.
We're in the demo lab with Lonnie, where he set up a photoelectric effect experiment. He has white light impingent on a metal, and the energy of the photoelectrons emitted are shown on the meter at right. If he puts a red filter in the path, now only red photons can strike the metal, and you can see they do not have sufficient energy to eject photoelectrons. If we go to higher energy photons, say go to yellow light, that's shorter wavelength and higher energy photons, they may be able to eject photoelectrons. And indeed, photoelectrons are emitted, but with a relatively small energy. If we go to higher still photon energy, green wavelengths, that's shorter wavelength still, higher photon energies, we can see photoelectrons emitted at a higher energy. Now we can still go to higher energy photons. Blue photons, photons in the blue region, are the highest energy visible photons, and Lonnie has a blue filter that will pass only blue photons. Putting the blue filter in the path shows photoelectrons emitted at the highest energy. So here's an example of the photoelectric effect. Thanks, Lonnie, for that great demonstration.
What the photoelectric effect does for us in this new atomic model is it allows us to start looking at light not only like a wave having wavelength or frequency, but it allows us to start looking at light as though it were made of particles as well. The German physicist Max Planck proposed the following relationship between a quantum of energy and the frequency of that radiation or of that light, represented by capital E is equal to H times frequency, or Planck's constant times frequency, where E is the energy measured in joules of that quantum of radiation. Nu is the frequency, again measured in per seconds, of the radiation emitted, and H is a fundamental physical constant, which we now know as Planck's constant. And Planck's constant is defined as 6.626 times 10 to the negative 34th joule seconds. A photon is a particle of electromagnetic radiation having zero mass and carrying a quantum of energy. The energy of a particular photon depends on the frequency of the radiation represented by this equation. And I'd like to point out the similarity between the equation that we saw on the last slide and the equation that we're looking at right here. They are in fact the same. This is how we calculate the energy present in a particular photon of light. And so when you saw in Lonnie's lab experiment these different photons of different colors having different energies, this is what he's talking about. The color that we are seeing as humans is relative or corresponds to a particular frequency, because that's why our eyeballs perceive them as different colors. And if they have different frequencies, they're going to have different energies. So now let's look at an example of how to calculate the energy of a photon using this equation.
We know that the speed of light and the wavelength. We also know the equation that relates the two things that we have with what we want, the energy. From here, we can fill in our knowns into the equation. We need to be careful about the same issue that occurred in earlier examples when converting between frequency and wavelength, though. We're given the wavelength in nanometers, and so we're going to need to convert that into meters before filling it in. If you're unfamiliar with the metric conversions, please review the material in your book and visit office hours for extra help to get you caught up on it. From here, we simply calculate and have our answer.
Now what you're probably thinking here is the equation that I'm seeing on the screen is not the equation that we saw in a previous slide. I will say it actually is, because 2 equations ago we saw that there was a relationship between the speed of light and then the frequency and wavelength of a particular wave. That's C equals lambda nu. The equation that I gave you on the previous slide was energy is equal to Planck's constant multiplied by nu. Well, I can rearrange the C equals h nu equation. I can solve that for frequency, for nu, and I'll have a statement of what nu is equal to. And so in this equation, E equals h nu, I'll actually substitute in speed of light divided by lambda for nu. So I'll make a simple substitution, and that allows me a situation where I can simply plug and chug. I have Planck's constant, 6.626 times 10 to the negative 34th joule seconds, multiplied by the speed of light. Yeah, that's 3.00 times 10 to the 8th meters per second, all divided by the wavelength of light measured in meters. Okay, I'm going to have to do. I'm going to have to transfer this unit of nanometers into meters before I can plug and chug, but once I do that, that's all it is. Use my calculator work, and I've generated an answer. All right, chemistry, this is where we're going to leave off for today. We are going to pick up with the hydrogen atom line emission spectrum next time we meet. I will see you next period.